Hello everyone, welcome to Canal Physics. In today's video we will learn how to subtract vectors. Before we start today's video, don't forget to buy your copy of Physics Foundations. Please click the link in the description below. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Now let's start today's topic. In the previous video, we learnt how to add vectors, and this was done using the head-to-tail method. However, to subtract vectors, we still use the head-to-tail method, and this is because subtraction can easily be converted into addition. Before we jump into this example below, it's important to know that the change in a quantity is the final value minus the initial value. And in physics, we use the lowercase Greek letter delta, which looks like a triangle, to denote the change in a quantity. For example, if you wanted to determine your change in height from Year 9 to Year 10, you would subtract your Year 9 height from your Year 10 height. So the change is always the final value minus the initial value. So in this example, we have a ball moving to the right initially at 3 meters per second. It hits the wall and bounces back to the left at 3 meters per second. And we're asked to determine the change in velocity of the ball. Let's add some variables to make it easier to solve this problem. So this 3 here is to the right, and that's the initial velocity of the ball. So I'm going to denote this velocity with v subscript I. So lowercase v is the symbol for velocity, and a subscript I denotes initial. And I'll do a similar thing for the final velocity, so I'll use f as a subscript instead, as so. Let's start by writing the change in velocity is equal to the final velocity minus the initial velocity. A common mistake at this point is to be tempted to put 3 into Vf and 3 into Vi, and therefore the change in velocity is 0, right? Well, that's wrong. Because if you do that, you're assuming that velocity is a scalar, which doesn't have a direction, but the direction does matter. So how do we mathematically incorporate the direction? Well, from the previous video, I'm going to use the common convention and say that rightwards velocities are positive and leftwards velocities are negative. And I'm just going to draw that in the top left over here to remind myself. And the change in velocity can't be 0, because if it was a 0 change, the ball would just keep moving in that direction. There wouldn't be a wall. That's what a 0 change actually looks like. But since the ball went 3 meters to the right and then 3 meters to the left, clearly there's some kind of change, so it can't be a 0 change. So substituting and considering my sign convention, the final velocity is -3 because it's 3 to the left, minus +3, which is just -3 there. So there's still a minus here because of the original equation for a change. But the value 3 here for Vi, that is a positive value. And this equals -6 meters per second. So the change in velocity is 6 meters per second leftwards. So remember, since velocity is a vector, then of course the change in velocity will also naturally be a vector. That's why we must quote the magnitude and units, 6 meters per second, but also the direction left. And just for further understanding, I'm going to draw this change in velocity vector over here on the original diagram, and that's the answer. Although we have the final answer now, I think it's worth spending time to explain this a little bit more, because you're probably wondering where the head-to-tail method is involved here. With one-dimensional problems like this, you probably don't need the head-to-tail method explicitly, but of course it was used, and I want to show you how it was used here. First, I'll do a little side note on the right. I hope we can agree that 10 minus 7 equals 3. But another way to write this is to go 10 plus -7 equals 3. Now this seems quite pointless, but we've done something very important here. We have introduced addition into a subtraction problem. So by the same logic, even though this is a change in velocity problem or a subtraction of vectors, we can still convert this into addition and therefore use the head-to-tail method. And this does become more important for two-dimensional problems, but I can still show you how it looks like in this one-dimensional problem, because it's always good to start simple. So let's redo the problem, but draw the vectors instead. So as before, the change in velocity is the final velocity minus the initial velocity, but let's actually draw these vectors. If we look at the original diagram, the final velocity is a 3 meters per second vector to the left, so I've just drawn that over here. And I've drawn the initial velocity vector over here. So using my little side example here to understand the next step, I am going to convert this subtraction of vectors into addition But when I do that, I must reverse or do the opposite sign of the thing that is subtracting away from the first value. In this example, that was 7. So I'm going to do that for the initial velocity here, the 3 meter per second vector to the right. So this subtraction problem can be written as addition. So 3 to the left plus 3 to the left, because I am making the second quantity opposite. So now I've got an addition of vectors. So I can use the head to tail method, and I'm going to join the head of this vector here to the tail of this vector over here, like so. You can see I've got this link or chain of vectors using the head to tail method. And as always, the resultant is drawn from the tail of the first drawn vector to the head of the last drawn vector. And I'll draw this with a red arrow. So this just makes it more visual to understand that the change in velocity is 6 meters per second to the left. And if this is still not making sense, I have one more explanation for you. Because some of you are probably still thinking, why is the change not 0? Well, just imagine being the ball. The ball is just moving along to the right at a steady or constant 3 meters per second, but then it hits a wall. And when it does so, it has to slow down. So it's going to go from 3 to 2 to 1 to 0 when it stops momentarily, when it's fully compressed. But then it's going to spring back out and speed up again to make it ultimately move 3 meters per second to the left. So it goes from 0 to 1 to 2 to 3. So we can see there's 1, 2, 3, 4, 5, 6 lots of changes, or 6 meters per second worth of change. Now let's do an example where we subtract vectors in 2 dimensions. So we're going to determine the change in velocity of the b, and the answer will be rounded to 1 decimal place. So here the b initially goes 1 meter per second north, followed by 1 meter per second east. As always, the change in velocity is equal to the final minus initial velocity. And since this is a 2-dimensional problem, we definitely need to draw the vectors to understand the answer. As we can see from the original diagram, the final velocity of the b is 1 meter per second to the east, which I've drawn here, and the initial velocity is 1 meter per second north, drawn over here. And don't forget, there is a subtraction of these vectors. Like before with the 1-dimensional example, we're going to convert this into an addition problem, but then we must reverse the second quantity, as so. So you can see I have made this 1 meter per second north vector into a 1 meter per second south vector. Now we can use good old head to tail, because we have an addition of vectors. And it doesn't matter which way you add them, you're going to get the same answer. I'm just going to join the head of the 1 meter per second east vector to the tail of the 1 meter per second south vector, like so. And I'm going to draw the change in velocity vector, or the resultant vector, with a red arrow as always. And because this is a vector, I need to define a direction, so I'm going to put a theta over here. And just a quick recap, why we put the theta on this angle here in the triangle and not the other side is because it makes more sense to define the direction of the vector where it's heading rather than where it's approaching. So that's why the angle must be subtended from the tail of the vector and not the head of the vector. Now it is clear that the magnitude of this change in velocity is the hypotenuse of this triangle. So 1.41 etc. meters per second. And theta is going to equal the inverse tan of 1 over 1, or opposite over adjacent. So 45 degrees. And 45 degrees makes sense because both of these lengths are the same. Before I quote the final answer, I'll draw the change in velocity vector on this compass here. So I've just added the values that we've solved, 1.41 and 45 degrees. And because it's 45 degrees, it's exactly southeast. So quoting my final answer, the change in velocity is 1.4 meters per second southeast. And that's it. Let's finish with one more example in 2 dimensions. Here we see a ball moving downwards at 9 meters per second, and then it hits a triangle and bounces to the right at 3 meters per second. And because this is down and right, this angle here between the dotted lines is 90 degrees. And we're asked to determine the change in velocity of the ball, round to 1 decimal place, and state the direction as an angle to the vertical. So starting with change in velocity equals final minus initial velocity, and drawing the vectors, and now converting the subtraction into addition, but therefore reversing the 9 to going upwards, and using the head to tail method, and drawing in the resultant, hence the change in velocity, and of course defining the angle, hence the direction. Now using trigonometry, we'll solve for the magnitude and theta. So our magnitude of the change in velocity is 9.48 etc. meters per second, and the theta angle is 18.43 etc. degrees. And we can see from this vector diagram that the change in velocity vector is to the right of the vertical line and it's upwards. So hence quoting my final answer. So the change in velocity is 9.5 meters per second at 18.4 degrees right of the vertical upwards. If this were a test or exam question, it would be worth 4 marks. 1 mark for determining the magnitude, 1 mark for the angle, and 2 marks for the final answer. And that's it. Thank you for watching this video. If you found it helpful, please like and share it and subscribe to my channel for more. Also, click the link in the description below to buy your copy of Physics Foundations. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Thank you.